It is the 4th of September 2025, approximately 12:36 p.m. Continuing off on the exercises from earlier. So, first of which, exercise 12. Let's have that exactly. Yeah, so we finished exercise 11. Back to exercise 12, which asks us to find the orders of the following elements. Of the multiplicative group Z mod 12, well, integers mod 12. So these are going to be the units of that, however, which are 1, -1, 5, 7, -7, and 13. Quick camera check to make sure everything's running well. And it looks like everything's going smoothly there. Not a lot of space in this one. Okay. So intuitively, how would you go about solving this? You would work modulo 12, reduce each representative to the set 1, 5, 7, well, 1 bar, 5 bar, 7 bar, 11 bar, the units of modulo 12, and compute the smallest positive k with which x bar to the k is equal to 1 bar. Squares collapse quickly here with 5 bar squared equal to 7 bar squared, which is equal to 11 bar squared, which is equal to 1. So how do we go about this more rigorously? Recall that the units of integers mod 12 is equal to 1 bar, 5 bar, 7 bar, 11 bar, and that -1 bar is equal to 11 bar here. -7 bar is equal to 5 bar, which whenever I say bar, I'm just saying modulo 12. So -7 to 5 bar, 13 bar is equal to 1 bar. So it's asking us to find the orders of each of these, right? So we need to multiply each of these by themselves to the point in which we can find exactly how many times does it take us to get back to the identity element. Well, if we look at 1 bar, what we'll find is 1 bar to the 1 is equal to 1 bar, which implies that the order of 1 bar is equal to 1. -1? Well, that's 11. Why is that? Well, we have here 11 bar to the 1 to the power of 1 is equal to 11 bar, which doesn't equal 1, but 11 bar squared is equal to 121, which is equal to 1 in this case, which is equal to the identity element we need. So the order of 11 bar is equal to 2, which from that follows that the order of -1 is therein equal to 2. So let's move on to the others. Yeah. So, looking at 5, 5 bar to the power of 1 is equal to 5 bar, right? So that's obvious, which is not, of course, equal to the identity element. Taking this squared, though, is equal to 25, which is equal to the identity element. Seems a lot more intuitive than, ones where we were looking to determine whether or not something was a group. But this is our rest period, I guess you could say. So 5 bar squared is equal to 25 bar, which is equal to the identity element, which is what we needed. So the order of that element 5 bar is therein equal to 5. Order of 7, take 7 to the power of 1, which is equal to 7 bar, which is not equal to 1 bar. So we take the square of that, we find it's equal to 49, which is equal to what we wanted, because 48. So ergo, the order of 7 is there and equal to 2. -7 bar is equal to -7 bar, which is equal to 5. And this is exactly the same as this here, which means that the order of -7 is equal to 2. Right. And 13, of course, well, that's just the same as 1 modulo 12, which means that the order of that is equal to 1. So, in conclusion, the order of each of these, 1 bar, -1, 5, 7, -7, and 13. So that's 1, 2, 2, 2, 2, 1. Pretty straightforward. Yep. So, for exercise 13, we're asked to find the orders, this one's a bit more. Okay. Orders of the following elements of the additive group. So this one's additive this time as opposed to being multiplicative. A lot more steps. Integers mod 36, which includes 1, 2, 6, of the following elements. Yes, this isn't units, so we're just supposed to find the units at the sorry, the order of each of these elements that it mentions explicitly. So the intuition for this is we are looking at the additive group integers mod 36 over under addition. The order of any element x bar is the least k greater than or equal to 1, with k times x bar equal to kx bar, which is equal to 0 bar, if and only if 36 divides k times x. The larger GCD between 36 and x is the fewer steps it takes to hit 0 bar. This leads to the standard formula that we looked at earlier. Well, it's different in this case because of the 36 there, but the general notion that the order of any element, multiplicatively speaking, is equal to the thing that you're modulating with respect to, so 36, that, and the element itself. So, let's say that more rigorously. So let's fix an integer x with, yes, x within the integers, and let d equal GCD. Well, it says necessarily fine, but we're looking at this rigorously to make sure that this holds up, and then we'll get into actually finding them. C of 36 and x. That's right. 36 is equal to dm, and x is equal to d times x prime with GCD of m x prime equal 1. Well, then we've looked at this before, right? But it doesn't hurt to look over it again. Kx bar is equal to 0 bar, which implies and is implied by 36 dividing kx, if and only if dm divides k dx prime. If and only if m divides kx prime. Now, since the GCD of m and x prime is equal to 1, the least k greater than or equal to 1 with m dividing kx prime is k equal to 1. Fair enough? So the order of x bar is equal to 36 divided by the GCD of 36 over x. So from here, we'd apply the formula entry by entry with negative a bar equal to the, well, bar over negative a. So this would be, well, let me just write this down. Negative a bar is equal to negative a bar. So the GCD of 36 and negative a is therein equal to GCD of 36 and a. How are we doing there? Pretty good. Right. So from this, let's go ahead and complete the table. So, the table of orders in the integers mod 36. So we have each of the elements that we mentioned earlier here. So 1, 2, 6, 9, 10, 12. Is that negative 1, negative 10, and finally negative 18. So what are the orders of each of these according to what we found? Well, 36, 18, 36, 18, 6, 4, 18, 3, 36, 18, 2. And we could do various checks to sort of, see what the hell is going on with this one. But, I mean, what you're going to find is that this is all pretty standard stuff and, holds up pretty well. We proved that it's logically consistent, and as we can see there, everything holds together pretty well. For 18, now for 4, it's 9, 36. And by the way, this bar symbol here, that's basically just in place to say, 36 mod 36. Don't know if I noted that, but in case it wasn't obvious, that's what we have. So, and this implies 12, order of 12 is 3, 2 times negative 18 is equal to negative 36, which is equal to 0 bar, so that implies negative 18 is equal to, the order of negative 18 is equal to 2, and as we can see, everything is consistent with what we've already laid out there in the table. let's move on to the next one. Problem 14. So these are all generally the same. Like, yeah, so for exercise 14, I'm gonna need a new marker here pretty soon. Find the orders of, yeah, we're in a multiplicative group this time, of the following elements of the multiplicative group. This time we're looking at the multiplicative group this time. 36. Integers mod 36. Units. So these would be 1 bar, -1 bar, 5 bar, -13 bar. Just the ones that we're looking at. -13. And 17. Units. Set of all residue classes. Set of all residue classes with degree 36. So, intuitively, work modulo 36 inside the unit group. So we have the set, which x bar is within the integers mod 36, such that the GCD of x and 36 is equal to 1. For each listed element, compute the smallest positive k with x bar to the k equal to 1 by explicit reductions. Probably useful to note here is that the absolute value of -1, I mean, not the absolute value, the way that modular arithmetic works is that -1 is equal to 35 here. That has order 2. 17 squared is equal to 289, which is equal to 1 in this case. 13 lands on 1 at the third power. So let's look at that intuition more rigorously and see exactly how that turns out. Right. So, proof. All computations are in integers modulo 36. Start with 1. So we take 1, right? Right, so let's use a different marker. So, there we go, that's better. I'll have to bring more of my usual ones. Okay, so we multiply by itself once, right? So exponent 1, and this implies that the order of 1 as an element is equal to 1. So moving on to -1. which is equal to 35 in this case, modulo 36. What did I say earlier? I might have misspoken whenever we were looking at the additive group. If I said multiply it by itself, that's not what I meant. What I meant to say was add it by itself. So, I mean, no. It's more so, yeah. We multiply it by a certain number, and that number would help us define exactly how many times we added it to itself. So, so we multiply it by a certain number, but in this case, we are in fact multiplying it by itself. So, -1 is equal to 35 in this case, and so order of 35, well, multiply it by itself once, that's not good, you don't get anything. So, how about twice? Well, you get 1,225. Now, if you separate that 1,224 plus 1, right? Well, that would get you 1, because 36, divide this, you can divide this by 36 to get something evenly, and you know, let's check the calculator, just for sake of curiosity, because I didn't write it down here. So, one 1,224 divided by 36, that is 34. Probably could have done that if I would have thought about it a little bit more, but so that's equal to 34 evenly plus 1. So we have ourselves 1. So the order of -1 then is equal to 2. Now let's go on to all of the rest of the elements, and hopefully we can fit that all within one writing of the board. So let's look at 5. Well, 5 squared is equal to 25, right? So that's not going to work. 5 to the power 3, 125 is equal to 125 minus 108, which is equal to 17. So that doesn't work. How about a fourth time? Well, we get that 17 times 5. Get about 85, right? And then so 85 minus 72 is equal to, because, 72. 36 times 2, 72. So we're allowed to do this little trick, which gets us 13, and that doesn't work. So how about 5 times itself 5 times, right? Well, we get 13 times 5. All right, so 13 times 5, which is equal to 65. 65, does that help us? Well, let's use that little trick again, this time with 36, and what we have is 29. So, no go. How about this? How about 6 times, right? There's better ways of going about this, but we're looking at this way. So, 5 times itself 6 times, 29 times 5, which is equal to 145, which is equal to 145 minus 144, and which finally gets us the identity. So the order of the element 5, in this case, is equal to 6. Right, that took up a lot more board space than I was anticipating, so. Now, how about for 13? Well, for 13 squared, we get 169, which is equal to 169 minus 144, which in this case is equal to 25. Well, it's equal to 25. So that's not going to work. How about, right, cubed 25 times 13 equals 325, which is equal to 325 minus 324, which gets us back to the identity element, which means that the order of 13 here is equal to 3. So, and second to last, negative 13 is equal to 23 in this case, and so we have 23 squared. What does that get us? Well, that gets us 529. 529, under this modulus we can subtract 504 from it to get 25, which isn't what we want, so let's go again. 5 times 23, which is equal to 575, which is equal to 575 minus 540, which is equal to 35. 23 times itself again, so we get 35 times 23, which is equal to 805, which is equal to 805 minus 792, which is equal to 13, not what we want. So we do it again. Times 23, 13 times 23, which is equal to 299, which is equal to 299 minus 288, which is equal to 11, not what we want again. So, but perhaps we're lucky on multiplying it by itself on the 6th go. So let's do that right now. 11 times 23, we get 253. Now let's do that trick again where we use modularity to our advantage. So subtract 252 from that, which gets us our identity element. So the order of negative 13 in this case, which is equal to the order of 23, is equal to 6. Now let's look at 17. 36 times what gets you 252? 36 times 7. So, 17, order that, 17 squared is equal to 289, right, because we already know the first one doesn't work, so 288, which is equal to 1. So the identity element 17, the order of 17 is there and equal to 2 for this multiplicative group. And what does that mean for this case? What does it mean for our table overall? Well, the order of 1 is 1, the order of -1 is 2, the order of 5, 6, 13, the order of that is 3, the order of -13 is 6, the order of 17 is 2, and therein completes the solution for exercise 14. Still running. Yep. Okay. Now we're stepping back into the more theoretical, less calculative substance of the matter, so this thing's out. Little by little, I'm running out of stuff here. Oh my gosh. This one's not even mine. Okay, so exercise 15. So, let G be a group. Prove that for all A1 all the way up to AN within the group G, we have the case that A1, A2, all the way up to AN, the inverse of that is equal to the inverse of, is equal to the product of its inverses, of its individual inverses for elements. So, to say that more directly, open parentheses, A1 multiplied by A2, on and on and on, up until you get to A sub n, close parentheses, to the power of -1 is equal to A sub n -1 times A sub n minus 1 to the -1, all the way up to A sub 1 to the -1. So intuitively speaking, to undo a sequence of moves A sub 1, A sub 2, all the way up to A sub n, we must undo them in the opposite order, with the opposite moves. First, A sub n to the -1, then A sub n minus 1 to the -1, before finally reaching A sub 1 to the -1. Group associativity lets us cancel step by step from the outside in. So, let's look at this intuition a bit more rigorously. Well, yes. Still going. I'd be surprised because storage space. Still works. Okay, so let's look into the proof of this matter. We prove the statement by induction on n contained within the positive integers, which, as you saw, could have been written as that, but we're writing it that way. I think like there's like this as well, so you can write that either way. Suffice to say, positive integers. The base case here, we say n is equal to 1, right? For any a sub 1 within G, we have that open parentheses a sub 1 close parentheses to the negative 1 is equal to a sub 1 to the negative 1. Right. Which matches the formula. What's the inductive step here? So assume the statement holds, right? Assume the statement holds. Assume statement holds for some k is equal to or, well, greater than or equal to 1, i.e. open parentheses a sub 1 times a sub 2 all the way up to a sub k close parentheses to the power of negative 1 is equal to a sub k to the negative 1 times a sub k minus 1 to the negative 1 all the way up to a sub 1 to the negative 1. That's our little inductive hypothesis. And I'm going to need more board space. So just move over here, check that it's looking fine over there. Yep, we're good to go. So let's continue along this line of reasoning. See where it takes us. So we have our inductive hypothesis. Now we prove it for k plus 1 elements. Right. A sub 1 times a sub 2 all the way up to a sub k plus 1. Right. Is equal to, open parentheses, a sub 1 times a sub 2 all the way up to a sub k times a sub k plus 1. Now here's where we have a nice group-specific trick. So we can use the group rule xy to the negative 1, open parentheses, xy, close parentheses to the negative 1 is equal to y to the negative 1 times x to the negative 1. Yeah, yeah. And that's by the induction hypothesis, right? So what we can then say is that open parentheses A1 times, all of them, all the way up to A sub k plus 1, close parentheses to the negative 1, is equal to A sub k plus 1 to the negative 1 times open parentheses A sub 1 all the way up to A sub k to the negative 1. Now, here's where the induction hypothesis really gets to say. We apply the induction hypothesis to A sub 1, open parentheses, A sub 1 all the way up to A sub k, close parentheses, negative 1. And what this gives us is open parentheses, A sub 1 all the way up to A sub k times A sub k plus 1 to the negative 1 is equal to A sub k plus 1 to the negative 1 times A sub k to the negative 1, open parentheses, A sub k to the negative 1 times A sub k minus 1 to the negative 1 all the way up until A sub 1 to the negative 1. And this is equal to A sub k plus 1 to the negative 1, A sub k to the negative 1 times A sub k minus 1 to the negative 1. And this goes on and on and on until we reach A sub 1 to the negative 1. Camera check. Camera's good. Now, this is precisely the required formula for k plus 1 elements. Therefore, by induction, the identity holds for all n greater than or equal to 1, such that we have open parentheses A sub 1 times A sub 2 all the way up to A sub n, close parentheses, to the negative 1 is equal to A sub n to the negative 1 times A sub n minus 1 to the negative 1 all the way up to A sub 1 to the negative 1. QED. Right. So let's go to exercise 16. So exercise 16 asks us to tells us let x be an element of a group G. Prove that x squared is equal to 1 if and only if the absolute value of x, the order of x, is either 1 or 2. So the intuition for this is, if applying x twice does nothing, so like x squared is equal to 1, then 1 or 2 applications already return you to the identity. The least such number is 1 or 2. Conversely, if the order is 1 or 2, squaring must give 1. So let's look at that a bit more rigorously. So it's going to take up a lot of board real estate. Right, everything seems to be working fine. So, we want to prove, we show both implications. First implication, if x squared is equal to 1, then the order of x is, the order of x is contained within the set containing 1 and 2. So, by hypothesis, x squared is equal to 1. By definition of order, the order of x is the least positive integer n with x to the power of n, x to the power n equal to 1. Now, since x squared is equal to 1, we have at least one such positive integer, and this is, namely, n is equal to 2. Right, so therefore, one is less than or equal to the order of x, which is less than or equal to 2. Hence, either the order of x is equal to 1 or the order of x is equal to 2, which is what we wanted. There we go. Let's put more on the board here. So now let's look at the other way around, because if and only if the order of x is equal to 1 or the order of x is equal to 2, then we have x squared is equal to 1. So if the order of x is equal to 1, then by definition x is equal to 1. So so x squared is equal to 1 squared, which is equal to 1. Right? Fair enough. The order of x is equal to 1. Then by definition x is equal to 1. That follows, tracks. So now it is itself the identity element, right? So if the order of x is equal to 2, then by definition x squared is equal to 1. Yeah, so yeah, this should be clear, but just in case, doesn't hurt to put that down, that x squared is equal to 1. There we go, x is equal to 1. And in this case, x squared is equal to 1. But the order here is 1, so x is equal to 1. In this case, it's literally the identity, so I guess I don't really need to put this down, but because, well, sorry. This x right here is just equal to 1, so, right. If the order of x is equal to 2, then by definition x squared is equal to 1. In either case, either way, x squared is equal to 1 holds. So, therefore, x squared is equal to 1 if and only if the order of x is within the set containing 1 and 2. There we go. These are less, abstractly structural? These are more concretely structural for now. Let's move on to 17. Don't really need this bottle anyway. So, question 17 says, let x be an element of a group G. Prove that if the order of x is equal to n for some positive integer n, then we have that the inverse of x is equal to x to the power of n negative 1. So what does this mean, really intuitively? Well, order n means x to the n is equal to 1. to peel off 1x from x to the power n, multiply by its inverse, x to the negative 1, on the left or right. Associativity turns into, well, x to the negative 1 times x to the n. So it turns that into, open parentheses, x to the negative 1 times x, close parentheses, times x to the n negative 1, which is equal to 1 times x to the power n negative 1, revealing x to the n negative 1 as the inverse. So let's talk about that more rigorously, again with a proof. Assume that the order of x is equal to n, because we only have to prove it one way. So by definition, x to the power of n is equal to 1. So let's left multiply both sides by x to the negative 1. What do we get? We get x to the negative 1, yes, x to the negative 1 times x to the n, which is equal to x to the negative 1 times 1. By associativity, open parentheses, x to the negative 1 times x, close parentheses, times x to the n minus 1 is equal to x to the negative 1. Now, yeah, since x to the negative 1 times x is equal to 1, the identity element, we obtain 1 times x to the n negative 1 is equal to x to the negative 1, which implies x to the n minus 1 is equal to x to the negative 1. It's equal to the inverse. There we go. Equivalently, right, multiplying, right, let's just note that. Equivalently, right multiplying works as well. So extend to the 1 by x to the negative 1 gives x to the n minus 1 is equal to x to the negative 1 as well. So, whoops, if the order, therefore we can say, if you didn't have to do this, well, I mean, it wouldn't hurt. Therefore, if the order of x is equal to n, then the inverse of x, x to the negative 1, is equal to x to the n minus 1. Q, E, Z. So, that's it for 17. How are we on time? Pretty good. So there's quite a bit to go. That's fine. So for exercise 18, let x and y be elements of a group G and prove that xy is equal to yx if and only if y to the negative 1, xy is equal to x, if and only if x to the negative 1, y to the negative 1 times xy is equal to 1. Y, x, if and only if y to the negative 1 xy is equal to x, if and only if x to the negative 1 times y to the negative 1 times x times y is equal. So the intuition here, x times y is equal to yx says x and y commute, right? So conjugating x by y measures the failure to commute. So if y to the negative 1 times x times y is equal to x, conjugation does nothing. So they commute, packing the same idea into a single element. The commuter, we haven't gone over commuters, but the commutator, x, this bracketed, x comma y is equal to x negative 1, y negative 1, xy equals 1, exactly when the failure to commute vanishes. So let's look at this a bit more rigorously and we'll see what we can do about that. Sometimes there's a bit of a sleight of hand in between what's actually a difficult problem for the writer of a textbook to make, just based on what people know versus on what's ahead. So, I mean, this is kind of a glimpse into what's ahead, but I don't know. It's hard to make a textbook. Relatively hard. There's harder things to do to write a textbook. Yep. So, to look at this more rigorously, we'll use a proof. We prove so we prove the three statements. This won't be as difficult as it looks. Are equivalent by showing x times y is equal to y times x implies y to the negative 1 times x times y is equal to x, which implies that x to the negative 1 times y to the negative 1 times x times y is equal to 1, which implies x times y is equal to y times x. So you see this whole little, I don't want to say circle because that implies circular reasoning when it's not. We're just showing that the implication flows both ways in a sense. It is sort of, it's logically consistent. It's a shortcut in a way, versus like saying, you know, you have to prove this and then this, you know, we'll get into it, but we're basically doing that. So, bleh, and then bleh. So, right? See, we're doing that. We're just including all of the little things that are in there. So, let's get into that. So let's start with xy equals yx implies that y to the power of -1 xy times x times y is equal to x. So we assume xy is equal to yx. That's something we're allowed to do, and then, well, that's what we started with. So left multiply by y to the -1. What does that get us? Well, that gets us y to the -1 times open parentheses xy close parentheses, which is equal to y to the -1 times open parentheses yx close parentheses. By associativity, since we're using group, by associativity, we have open parentheses y to the -1 times x close parentheses times y is equal to open parentheses y to the -1 times y close parentheses times x. Now, probably see where this is going, but since y to the -1 times y is equal to 1, and 1 times x is equal to x, we obtain y to the -1 times x times y is equal to x. Yep. Oops. Go. Now let's move on to another step. So we move on to the case where y to the -1 times x times y is equal to x implies, we want to show this, implies x to the -1 times y to the -1 times x times y is equal to 1. Assume y to the -1 times x times y is equal to x. Left multiply by x to the -1. What does that get you? Well, x to the -1, open parentheses, y to the -1 times x times y, close parentheses, is equal to x to the -1 times x. By associativity, open parentheses, x to the negative 1, y to the negative 1, close parentheses, x times y is equal to 1. So, x to the negative 1 times y to the negative 1 times x times y is equal to 1. So, move on to the next step here. Right. See that? Right. Now, solve another thing. So we're almost there. We want to show that x to the negative 1 times y to the negative 1 times x times y is equal to 1. How that implies that x times y is equal to y times x. Well, assume x to the negative 1 times y to the negative 1 times x times y is equal to 1. Left multiply by x. That gets you x times open parentheses x to the negative 1 times y to the negative 1 times x times y, close parentheses, is equal to x times 1. By associativity, so in case you're not noticing a pattern with how we're doing this, but by associativity, open parentheses x times x to the negative 1, close parentheses y to the negative 1 times y to the negative 1 times x times y is equal to x. Which implies 1 times xy is equal to yx. Whoops. Let's see this by associativity. No, we haven't gotten to that step yet, sorry. By associativity, is equal to x, which implies 1 times y to the negative 1 times x times y is equal to x, which implies y to the negative 1 times x times y to the negative 1 times x times y is equal to x. Now, left multiply by y. So y times open parentheses y to the negative 1 times x times y close parentheses is equal to yx. Again, by associativity, open parentheses y times y to the negative 1, close parentheses times x times y is equal to y times x, which implies 1 times x times y is equal to y times x, which implies x times y is equal to y times x. So the three statements are therein equivalent. Let's just write that here. xy is equal to yx if and only if y to the negative 1 times x times y is equal to x if and only if x to the negative 1 x to the negative 1 times y to the negative 1 times x times y is equal to 1. There we go. So we are done with 18. Now we can move on to 19. Well, actually, we're a bit out of time. How long is 19? Can we prove that? 19's a long one. A longish one. It's not too long, actually, but I don't know if I have the time for that today. Well, right now. Yeah, okay. Let's go ahead and stop here for now. Reconvene and discuss that one, the rest of them later. Well, some more later. And that is it.